Hello, and welcome to VSkap Science. I'm David, and today I'm going to be showing you guys a cool trick that uses torque, friction, and a couple of other different concepts. Now, this trick can be done with any long, fairly straight object. Now, I'm using a piece of wood. It's nice and easy. It might be a little splintery, so that's why I've got gloves on. Now, we are going to find this piece of wood's center of mass. Now, to do that, well, first you need an approximation. You need to put your hands outside its center of mass. So you could try this with a baseball bat, with a tennis racket, a rake. As I said, pretty much any long, straight object. Now the way you do it, as I said, put your hands outside its center of mass. And then what you're going to do is just slowly try to bring your hands in. What you might notice happening, sometimes one of them is going to move, sometimes the other one's going to move, but they'll end up meeting just about in the object's center of mass, which for this piece of wood looks like it's about there. And I can prove it because I'm holding it there and it's not really tipping to either side. Now if I were to hold it somewhere else, say right here, it would definitely tip. So that's how I know I haven't found its center of mass. Now this piece of wood is nice and straight and it's even, and its center of mass is probably just about halfway. But we don't need something that is very even like this. So now I'm going to take this book, I'm going to put it on one end. Now that is definitely going to affect its center of mass. So let's see if our trick will still work. So I've got both my hands away from where I think the center of mass should be. I'll just bring my hands in. And now my right hand is going to be moving for a lot longer than my left hand. But as it turns out, they're meeting somewhere right about there. So the center of mass should be just about there. And as you can see, this book is not falling. The other side, whoop, well, okay, I just about found the center of mass, but not quite, you know. Books are a heavy thing and center of masses are pretty delicate. But now let's go back to the board and see why this might happen. The two things we really need to know to understand how this works is torque and friction. Now, I think the best way to figure out torque is through thinking about a door. So, on a door, we have a big, long object, and we have a pivot point. Think of it like the hinge of the door. It'll rotate there, but the hinge itself won't be able to move at all. Now we have a pivot point, and we have somewhere we are applying a force, and that force is going to be some distance away from the pivot. Now, if you were to try to open a door, would you use the doorknob that's really far away, or would you try to push very close to the hinge? Well, you guys have opened a couple of doors in your life. I think you would know the more effective way is to use the doorknob that is far away. That is because the further away you are from the point of rotation, the more rotation you can have with the same force. If you have 10 newtons here and 10 newtons there, you're going to be rotating it much faster if you apply those 10 newtons right there. So that's torque, and it's normally represented with a tau. Now, what about friction? Well, let's say we have an object, just got a little cube here, and it is sliding along this way. So, at the moment, there's no forces on it, but that's not entirely accurate. If nothing else, there has to be gravity. So this is gravity, or the force due to gravity. And then, well, our block is not trying to fall through the ground. It's actually going to be on the surface, sliding along. So that means there is some contact force. I'm going to label it I can't actually write anything, but there we go, the normal force. Now that normal force on a horizontal plane is going to be exactly equal to gravity. That's going to stop anything from falling through the ground or flying up into the air. Now we said it was moving this way, but assuming this is the real world, there's going to be another force on it. Because if I take this piece of wood, and I put an eraser on it, and I just go woo, woo, it will eventually stop. Actually, this will stop pretty quickly. Now, the force that was stopping it is the friction force. So if the motion was this way, the friction will be pulling it this way. And I'm going to label that as force of friction, or FF. Now, the force of friction is actually a retardant force. It will go against whatever motion there is, no matter what direction that motion is. If there is friction, it will be against the direction of motion. Now, friction depends on two things. It depends on the coefficient of friction, which is just a number. Normally it's between 0 and 1, but in the high end it can be above 1. And it just represents, in my eyes, how rough the two surfaces are. So if we look back again at the eraser and the piece of wood, the eraser stopped very quickly. So there is a high coefficient of friction between these two. Now, there are different coefficients of friction for all types of materials. Wood scraping against wood is different from wood scraping on concrete, and that's different from ice skates going against ice. Now, we have the coefficient of friction, and the last thing it depends on is Fn. Now, Fn is this normal force. Now, you might be thinking, why don't we just use gravity if they're the same thing? Well, if you have some sort of incline, which I'll cover in another video, your Fn will not be in this direction. It'll actually be up that way, and it will not be equal to gravity. But that's not what we're talking about at the moment. Point is, we use the normal force to figure out friction. So, from there, I think we've got everything we need. So now, let's go back to our piece of wood and see if we can piece this all together. Now that we know about torque and friction, we can apply it back to the piece of wood. Now, let's see if you guys can think about it. As I'm putting on the gloves, I'll start the explanation. Let's see if you guys can stay one step ahead of me. Now, when we talk about rotation, we talk about clockwise and counterclockwise. So that's how I'm going to be doing it. Now for me, if I look at it, this, to me, is counterclockwise, but to you, that should be clockwise. So hopefully, I'll be able to flip it around for you guys. If for some reason I mess up, hopefully I don't, I'll let you know in the description. Anyway, we have our hands about equidistant from the center. So at the moment, we'll cheat and know that the center is about in the middle of this piece of wood. Now let's look at the different torques going on. So let's look at this end. On my right end, we have a very large torque going this way. And that torque for you guys is clockwise. Yeah. So we have a very large clockwise torque and a very small counterclockwise torque. Now let's look over here. Well, we have the opposite. We have a very small counterclockwise torque and a large clockwise torque. However, these two huge clockwise and counterclockwise torques are just about going to balance each other out. So the only torques I really have to fight with my hands are these small ones. But now, as I bring my hand in, something changes. The amount of torque will increase. All this, now I have a whole lot more of this is clockwise for you guys. No, it's clockwise for me, so it's counterclockwise for you. So we have a very large counterclockwise torque. That is actually going to push on my hand even more. And that pushing creates a strong normal force. Now, we just said friction depends on the coefficient, which will not change, the gloves to the hand, and the normal force. So now we have a larger normal force on this hand than we do over here. So if I try to bring these both in, one with less friction is going to move until it has a greater normal force than my hand, and they end up meeting at the center of rotation, which is the center of mass. Now, if I were to throw this, A, I would cause a lot of damage, but B, it would end up spinning about its center of mass. And if you take a hammer or something with a drastically different center of mass, it will always spin around that center. And if I were to tape this book to my board and I would toss it, if this is about our center of mass, it would rotate about that center. That's just a unique property of all objects that have a center of mass. And now that I think about it, all of them do. Even something like a hoop. If you have a ring, the center of mass is not actually going to be in the object, it's going to be in the middle, but it will still rotate around that center of mass. Now, speaking of the book, let's take a look and see how the book will affect all this. Now, I think you guys can already figure this out, but just in case, at the moment, we have a very large amount of force that is, I need to hold it, that is just in this little section, because the book is so much heavier that incurs a much greater normal force on my left hand than on my right. So my right is free to come in a very large distance before the normal force on one side is equal to the normal force on the other. And they'll meet in the middle, and I don't want to drop the book again. But anyway, that's a neat little trick. As I said, it works with any long straight object that you can move your hands up and down. Baseball bats, tennis rackets, hatchets, anything you can think of. Big pieces of wood, tripods, anything you want, that will work with. And that's a little secret you have been taught. I hope you guys like this video. If you like it, it would be awesome if you left a like or even subscribed. You never know. And if there's anything specific you guys want me to cover, let me know. You can comment it to me or you can DM me on any social media. I've already got a lot of ideas, but I will prioritize any that are requested. Alright, stay cool, stay tuned. I know this wasn't as flashy a video as last time, but I hope you weren't too bored.